Welcome again to Computer Vision online classes. In the last class, we started this parameter estimation and we first discussed about linear least square fit. Then we have noticed some of the issues that we encounter while using the linear least square fitting for estimating the parameters. Then from there, we moved on to RANSAC, random, which is based on the random consensus. So this is where we stopped in the last class with the question that you have how many samples you need to choose such that with a, let's say, a probability of E, which could be, for instance, 99% probability. Okay, you could be, for example, 0.99. We should be able to say that we have the right fit or right set of parameters we have arrived at. And the equation we said is this. So let me again mention what are these variables. So E is telling you that how many percentage of outliers do you have? Let's say it could be, for example, out of all the set of values that you have, that you are obtaining from each set of minimum set of required points to obtain the parameters, that E is giving you the percentage of outliers. Okay. So for example, 10%, 20% or something like that. And S being number of points you need to pick in order to get the parameters rightly, or in order to get the parameters. So for example, if you are fitting a line, you need at least 2 points. So in that case, for example, S turns out to be 2. Okay. And suppose, yeah, accordingly it varies. Let's say you are doing a homomorphic transformation, there 8 sets of points are required. So that S turns out to be 8 there. A fine transform, for example, if you are doing, S turns out to be 6 because you need 6 sets of points. And capital N turns out to be number of samples. Be clear with this capital N. This means, in another way, number of times you need to repeat this experiment of picking the samples. That's what N tells you. It is not the number of points. Be clear with that distinction. N is number of times you need to pick the samples. That's what is given by N. And let's say you want to say with 99% of probability that now you have the right parameter estimation. Okay, there in that case, P is the desired probability of getting a good sample. And then we left the last class on contemplating about, asking you to contemplate about how we arrive at this equation. Would anybody is able to give some try here? E
E
represents,
probability of an outlier. So,
yeah, E represents probability of being an outlier. Correct.
we can have 1 minus E as probability for an inlier.
Very good. Right.
Uh,
And
we have
then,
S number of points in that sample. So if we take S points, so it's 1 minus E.
so what is this probability now? 1 minus E whole power S. What does that give? The
So
probability of,
S inlier points.
very good. In other words, since the points in a sample itself is S, you could say that the probability that a given sample has all inlier points. Is it not?
Yes, sir.
Very
Yes.
good. And now, what does this represent now? 1 minus of E power S.
It is complement of the previous one. That is, we have at least one outlier in this.
Yes. So you are, for example, you are doing a homomorphic transformation. You need to pick 8 points for that. And this would give you the probability that out of 8 points that you have picked, you fill the gap after that. This gives you, I need to pick 8 points, assume that. So my S is here 8. Okay. Now 1 minus of 1 minus E whole power 8 will give me the probability that out of the 8 points I have picked, what is that? The probability that
out of those 8, maybe one or more were outliers.
Very good. It is giving you the probability that one or more are outliers. Correct. What does this whole power n would give me now? Where n is number of samples, such samples I am picking n such samples. Okay. Now what does this give?
So I picked n samples in
Hmm.
which none of the samples were pure. Like every sample had one or more outliers.
Excellent. Very good. So that would be equivalent to what then? Your P is probability that a point is P is a probability that you get a good sample. Okay.
Uh,
So now what is this going to give you? Probability that
uh, the expression which we have got is the probability for a bad sample, and its complement will give me a good sample
very
probability.
good. So this is equivalent to 1 minus P. Is it not? The probability that we got all samples are bad out of n. Is everybody with this? If you have not understood any part of it, right time to clarify that.
Yes, sir. Could you just explain this once more?
Yes, sure. See, first think about a single sample. Hmm. In that sample, I have S points I am picking, assume that. Now, what is the probability that all S samples are inliers? So that means that is equivalent to, since the probability of an outlier is E, probability of getting an inlier in one experiment is 1 minus E, and you have to get next one also should be again here make another assumption that without you will not be picking the same point again. So to be strict you need to reduce your sample size by 1, but the implicit assumption here, which is makes perfectly sense here, is you have a lot of set of points even without replacement, and reducing it by n, reducing n by 1 would still be of the same size. That's you with, although you are doing without replacement. Okay, for those you should be knowing it from your probability without replacement. Even if you are doing it, the size of your number of points is so high that it doesn't really change picking 1 or 2 points there. Okay, coming back with that, 1 minus E is the probability that the point you picked out of a sample, out of the whole points, is a inlier. And now you are picking S points, all points being inliers is 1 minus E whole power S. Now when the probability of having at least one outlier, at least one means there could be one outlier or more outliers, that how do you get that? That's nothing but, the only exception to this is all being inliers. That's the only exception. Out of all the rest of the cases, to get it, you subtract it from 1, the maximum probability being 1. That would give you that among the S points that you have picked up, there is at least one outlier. Is it clear so far, this part? You are repeating this experiment n number of times, right? And the probability that you see, the case is when are you going to fail? You are going to fail when all these n experiments are giving you, in each of those n experiments, if you are getting at least one outlier, it's a failed case. So the probability of getting not even a single good sample is nothing but 1 minus P. And that's of course equivalent to, you get this every time out of n. So just like you did here, 1 minus E power S, this is this whole power n now, as you are repeating this experiment n number of times. I'll show you the same thing here. 1 minus E is giving you probability that choosing one point yields an inlier. This 1 minus E whole power S is giving you probability of choosing S inliers in a row. Okay, and 1 minus of 1 minus E whole power S is giving you probability that one or more points in the sample were outliers. That means your sample is contaminated, and that whole power n will give you that all n samples are contaminated. Okay, so if the 1 minus of that would give you at least one success, or you could write this is equivalent to, since P being the desired probability that we could take good sample. So notice here, if I'm doing this experiment of picking sample S samples n number of times, it is good enough if I am successful once. That's good enough for me, is it not? Because you would be looking, you will be picking those set of sample for which you have maximum number of inliers. Okay, and that case this is good enough. So you have the luxury to fail every time except once. That's good enough for you. So that's why this is equivalent to this, or I could have written this directly equivalent to 1 minus P, because this is the only case when I would be failing, and P being desired probability of getting a good sample. So the desired, the probability of getting a bad sample would be equal to 1 minus P. Okay, or you could interpret it in slightly different way. 1 minus of this will give you probability that at least one sample was not contaminated. This is the probability that, if you see, this is the probability that all n samples are contaminated. If you want the probability that at least one sample was not contaminated, you would do 1 minus of that. Okay, and that would give you P. Clear so far? What is the objective of writing this equation, or how could we profit from this equation?
Yes, to determine the optimal values of S and N for a given
We
P.
need to determine the optimal values for yes. What is S here?
No, S is, we can take 2, sir.
Yeah, see, S is fixed here. Suppose if you are looking for fitting a line, right? This S equal to 2. As I said, suppose if you are going to compute an affine transform between two images, then your S is there, say 6, right? And if you are doing a homomorphic transformation, this is equal to 8. So S is fixed. So what is the only variable? So P, you would say that, well, I want with 99% probability that I have at least one right picking of the samples, in which all the points that I have picked in a sample are inliers. That's the P. So we could fix the P like I want it with 99% probability. Okay, that is done. E is telling you, for example, the probability that a point is outlier. This information comes from your experimentation, where you could say, well, I should not be having more than 50% of outliers. Okay, that cannot be determined from here, but rather comes from the information of you on how good your samples are. Okay, and S is anyway fixed. So only thing that's remaining here is N. So how do you compute N here? So let me take this onto the other side. So I would get 1 minus P equal to 1 minus of 1 minus E whole power S, right? And whole power N. Take logarithm on both sides. I think log to the base 2 if I'm not wrong. I need to check that out, but doesn't really matter. N log 1 minus of 1 minus E whole power S. So that means my N equal to logarithm of 1 minus P by logarithm of 1 minus E whole power S. Now, if I, let's say, I want to fit a line, so my S equal to 2, I want to say with a probability of 99% that at the end of this entire experiment, I have at least one good sample. So my P is, for example, there 0.99, and I have at I have sorry I have at most 50% of outliers. So my E there is 0.5. Given them, I could compute N, and that is the number of times I have to pick the samples. That's all. This is as simple as that for this RANSAC algorithm. Yeah, this well, I could actually if I'm there is no this is the minimum number of times I need to pick samples, and of course my N could be greater than that. So if you use that inequality there in your equation, you'd be getting there N greater than log of 1 minus P by log of 1 minus of 1 minus E whole power S. That's all. So the same thing now, again put it in a proper order here. A given model has a minimal set, the smallest number of samples from which the model can be computed. So this is your equal to your S value. Image transform, so line for example 2, okay. Translation, you just one point pair is good enough for translation. Homography, yeah, I told it 8, but that's in fact equivalent to 4.5. Sorry, homography 8 you need it. So you require essentially, because you get two equations from each of those points. So 4-point pairs are required. So if I am not wrong, for a fine, you would require 3-point pairs. Line 2 points, right? 2 point, yeah. Anyway, this is a different thing. So this is a kind of line fitting. That's what we are looking at. But now you could see same thing for obtaining image transformation. Okay, that's a simple thing to begin with. So that's why we started with that. Now the algorithm would be randomly select S points from a sample, instantiate a model, get consensus, set Si. If that is greater than T, I'll talk about it in more detail, but hope it is clear so far before I move forward. And for example, I am giving all these explanations based on the line because that makes our life easier to understand. Just 2 points, so imagining is easier. But again, you could see the same thing in terms of point pairs when it comes to the transformations. Okay, there is nothing like a, when fitting a line, there is no point pairs coming there. It is only when you are doing a transformation that concept would come there. And now there is something else also here, which we assumed actually implicitly, is how do you consider something as an inlayer and something as an outlier? That only will tell you how many inlayers are there and how many outliers are there. One common thing that has been done is you assume a Gaussian distribution here over that, and again you assume that you know the mean. But otherwise in practice, most of the times we have no clue on how much noise is there or what is exactly the noise. So in those cases, you make some assumption of some sigma value there, right? And based on that, you would be so f of t, so that you could now tell based on that, well, it is a, if it is a 1D case, that's a Gaussian distribution. Had it been more than that, one dimensional case, you have something called as chi distribution with k degrees of freedom. So that's what you would use. You assume something there, okay, for sigma value, and from that you could say whether it's an inlayer or outlier. So this is some other information you also would require to make a classification of inlayers versus outliers, right? So choosing the parameters, some of them are already clear to you. Number of points in the sample S is typically minimum number of points needed to fit the model. Then distance threshold is, well, choose T. Probability for inlayers is high. Say, let's say you could say 95%, yeah, choose T. So probability for inlayer is high, zero mean Gaussian noise with standard deviation. So yeah, you would make some assumptions here on what exactly to be done. So what is your T value that, yeah, if you assume a Gaussian distribution with variance sigma, then what should be the T value such that you would consider it as an inlayer? I would prefer skipping that part, since I'm sure you have that intuition now on what exactly to be done there. Then number of samples n is chosen, that with probability p, at least one random sample is free from outliers. So for example, you could choose with 99% of probability you want to say something, right? As per the above calculation, n is kind of 99% probability you would be saying it. But do you think there is any means to terminate the whole process without even running the whole thing for n number of iterations? Can you think of any scenario where you could detect that this is the right solution and you stop the iterative process there itself? Is there any way of doing that? Can you think of any such scenario on how you can do that? Is my question clear? See, ideally I need to run this n number of times, okay, such that with 99% of probability I have at least one good sample, right? But do you think any instances, or do you think whether you could detect in between at the end of, let's say, every given iteration, whether you are already having a good sample so that you could terminate it there itself without going for the rest of the iterations? Can you think of any such scenario or any such way of doing it?
If E is very low, then we have high probability of having inliers.
What is E here?
A probability that a point is an outlier.
Point is an outlier. Now, Mike, maybe you are, I think you are around the bush. I need to still beat the right point there. Is there any way? Suppose I give you, okay, one set of points, and I got some parameters for it. Given those parameters, is there any way to assess what is the number of inliers and outliers for that particular set? Is it possible? See how I do. Just imagine the whole flow. I pick a sample of, let's say, I want to fit a line. I pick 2 points, right? Now, after I pick 2 points, I set, I find out the parameters for fitting the line. For example, slope and intercept, I compute from those 2 points. Now I have a line, okay? Now I would know, I know that which can be considered. Do I now not know which are the inliers and which are the outliers for this line fitted? Is it not possible? Of course, yes, because you, let's say you say within a distance of let's say 2, okay, distance of Euclidean distance of 2. If the point is there, you consider it as an inlier, otherwise you consider it as outliers. Now, given that, can you not compute the percentage of outliers there?
So what we can get the number of inliers
Right.
from looking at the margin, and the percentage is just that divided by total number of points.
That's all. That would give you the percentage of inlayers. 1 minus of that, okay, or 100 minus of that would give you percentage of outliers. You are making an assumption. Suppose I got my inlayers as 90%. Okay, I am assuming there the probability that a point is an outlier, 50% of my points are outliers, I assumed, for example. But I got 90% of inlayers for this. So definitely that's a very good match. Is it not?
Yes, sir. And
So
we
I
can
could
stop
stop
there.
there. Okay, even better. Can you improvise this further? 98% of your points are inliers and only 2% of outliers. Quite possible. So is there any way you could address this now? That's the next follow-up question to you. So you will also update the value of n here, given the new value of E. Okay, anyway, P is we want to say with 99% probability. S is number of points in a sample is fixed. So suppose you started for the earlier one when your E is very small, you might be having some 1,000 iterations to run. But the moment your E has increased, you already got a 90% now. So your N will come down now. And for every time when your E is increasing, or your number of inlayers are increasing, you accordingly update N, and that's the number of iterations for which you need to run. Okay, this is yet another improvisation of the random consensus algorithm. So it is something like this. In a class, okay, suppose only 50% of mischievous, so 50% of mischievous students are there. I need to pick 2 students and none of them should be mischievous. Okay, I'm now randomly picking the students from there. Consider a case, how many times should I pick 2 students randomly, such that at least there is one case where both the students I have picked are very good sincere students. So as the number of mischievous students in the class are increasing, I have to repeat this experiment of picking 2 students a lot number of times. Suppose if I happen to know that 90% of the students in the class are very sincere, so the number of times I need to pick such that with a 99% probability that at least in one sample of my picking of 2 students, I have very good sincere students, is number of times I have to do this would come down. Is it not? In the similar lines, once I am getting the parameters, every time I am reassessing how many inlayers are there, how many outliers are there, that I can do. Okay. And once I do it, now my earlier assumption of my percentage of outliers can be updated. Maybe initially I thought that in this class 50% of the guys are mischievous. Okay. Then I realized for a after doing this experiment, and there is a way to compute whether the two whether percentage of outliers and inlayers, and then I figured out that, well, 70% of the students are very sincere and very hardworking. If that is the case, then what will happen? Number of times I have to pick, well, I don't have to pick 100 times. It's good enough if I pick 17 times. Then next time I figured out that 90% of the students are very hardworking and sincere. So then that could further come down. Well, it's enough if I do this experiment 20 times. So this is what actually adaptive, they call it as an adaptive procedure, adaptive RANSAC. This is yet another paper that came, I guess, later, where they start with n equal to infinity. Either you could start with something like, see, if the number of outliers are more than 50%, that's the very bad scenario to be in. You can't really expect any fit there. So it's not a bad idea to start with 50%. And every time you look at the e value that you are getting there. Okay. And if your e value, what you are getting here, is more, if the percentage of e, is it percentage of inlayers or outliers? I forgot. E is proportion of your outliers. If your proportion of outliers are less in a given experiment, then you update that now, so that then your n will come down, and just run it for so many experiments. So in this adaptive algorithm, sorry to just jump, but that would help you to connect it quickly. You start with some value, you don't really know what is n, you just start, you randomly first pick one sample. For that sample you do a fit. Okay. Anyway, first time whatever you are getting as outliers, that would depend what is your n value, which you compute here. Okay. Based on this e value, from next time onwards, what you do is, every time at the end of your experiment, you recalculate the value, that percentage of inlayers you are getting for that particular experiment. And if that percentage of outliers are less than the previous outliers, okay, given by e naught, then you replace your e naught value with this, and accordingly calculate n, and you update that n value here, and that would reduce or adaptively adjust the number of times you need to conduct this experiment.
How would you choose the value of E in that case?
Yeah, see, that's what you just use 50% and go ahead. You just assume that I have 50 out of 100, some out of 100 points I have, okay, 50 points are in layers. The fit should be such a way that it should, for that fit, at least 50% are in layers. That's, so you empirically fix the value of E, in other words. There is a very interesting observation you could make from this equation. I'm not sure how many of us made that. How is it dependent on the number of points I have? Can anyone give it a try? So I have, for example, I want to fit a line. I have 100 points. In there is another case where I have 1000 points. So how is my algorithm's computational complexity is going to change if the number of points I have is increasing, or to put it in the context of transformations, number of point pairs I have is increasing. So how is the computational complexity of this algorithm is going to change? Is case A, I give you 100 points, okay, for which you need to fit a line. Okay. In case B, I'll give you 1000 points for which you need to fit a line. That's why initially also I gave an alert that this n is not number of points. That's number of times you just need to repeat the experiment.
Then it won't change. As
That's
long as
right.
E is fixed, it won't change.
That's right. This is somewhat counterintuitive to begin with. but then it perfectly makes sense because we are saying that however big might be the number of points, but we are in terms of proportion, it has same number of outliers, same percentage of outliers in both cases. So given that constraint, number of times you need to repeat the experiment would remain same unless the probability changes with the incoming points. But if the proportion of outliers is same in both case 1 and case 2, despite having 1000 points instead of the initial 100 points, the number of iterations required to fit a line is going to be the same. N here is number of times you need to repeat the experiments. So this is what we want to compute. How many times I need to pick these points randomly? I pick once 2 points, okay, and then compute inliers, outliers, fit that, get a parameter. Second time I again pick randomly 2 points, repeat this experiment. So this number of samples I need to pick or number of times I need to repeat this experiment of picking a sample is capital N. But what is more important is among the whole number of points you have, as long as the proportion of outliers is same, let's say 50% of outliers are there, this is not going to get affected with the number of points you have.
Sir, could you go to that adaptive algorithm?
Right. Yeah.
Yeah, here, how exactly is this? Like, if we choose a particular sample, and from that particular sample, we are trying to count the number of inliners. What exactly do you mean by that, sir?
Okay.
Like the points
See,
which are associated with that
right.
particular
See,
sample?
for example, I have lots of points here. Okay. These are all points I have. Now, I got this is the line that got fit. Okay, I picked 2 points, for example. Those 2 points happen to be these 2 points. I have fitted this curve now. Okay, now what I will do, I know that within this region, if this is within this of this line, okay, all the points which are there within that region I would consider as inliers. So for example, 1 2 3 4 5 6 7 8 inliers are 8 for me, outliers are 3 for me. Okay, so percentage of outliers are 3/8 for me.
Yes.
Or 3/11 perhaps, not 3 by,
Yeah,
yeah,
3 by
3/11.
11.
Is that's how I compute E value.
Okay. So
And
is it more like based on the threshold which we have fixed, which
yes,
we are going to
yeah,
fix,
that
the
comes
E is
from
going
the
to change?
noise model. See, from the noise model you assume that, well, there could be, from the actual fit there could be some diversion of so and so. That's where the noise model comes into picture. That tells you this within which values of I should consider it as inliers.
So it's more like the E which we had earlier is more like the prior probability, and we are actually verifying it with the samples which we have taken.
See, earlier we were assuming E. See, what is the role of E? The role of E is just to tell you how many times you need to repeat this experiment is what is the role of E. That's all. So
Okay.
earlier we took an extreme and saying that there are 50% of outliers in my case. Half of my samples are screwed up samples. Okay, I have only 50%. So how many times should I run this experiment? You are taking that and running that experiment without really, you are not further looking back and seeing, well, for a particular set of points, how many inliers and outliers did I get? And based on that, is it really 50% outliers are there? I am never looking back. I'm never introspecting there. This adaptive
Got it, sir.
algorithm would do one more step here of introspection and fine tunes that E value. So then it says, look, actually we started with 50%, but it's not really 50%, 90% of inlayers are there. So with given 90% of inlayers, my N need not be so high. I just need to run this whole thing. Let's say initially 1000 I thought, but 800 is good enough. That's what my N. So now I would repeat this experiment while this loop count, sample count, I will do only to 880 times. That's all. Other
Got
than
it.
that, there is no effect of it. Okay, is that clear?
So that's why the N is independent of number of samples we have. I mean, the
Correct.
number of points we have, but it depends only on the ratio.
That's right. That's right. So just a few more things before we conclude this topic of parameter estimation is look at the effect of number of samples and proportion of outliers. Okay. So for example, let's look at first row wise. I fix, for example, I have two pairs of points or 2 points in case of fitting a line. So I know S value. Now, how many times I need to repeat this experiment? So I'm going to compute N, but I should now also saying, for example, I should be able to say whatever I'm going to say with 99% probability. This is the best fit. This is the right fit. That's what I want to say. So I have the p value also fixed there. But what I'm changing is if my noise is increasing, how the number of how the number of iterations that I need to run is going to get affected. That's what this is going to take a look at. You could see here, I started with 5% noise, 10, 20, 25, 30, 40, 50. As I said, more than 50% of your samples are noise. Doesn't better don't fit anything there. Okay, so we stop it there to 50%. What is very interesting is so you just simply need to substitute these values here and see it. What is very interesting here is that please check here. You do the calculation later after this class. I I vaguely remember it as log to the base 2. So please check that out because you could calculate this table yourself using a calculator itself. So please do that and let me know next class. I don't remember it and I would give it to you. Or maybe even if you take another logarithm, I don't think it is going to change these values. Okay, that's something I want you to check out. Okay, coming back here. So it is not increasing very drastically here. So same case here. Suppose I have three parameters. So I need to pick 3 points, for example, or 3 point pairs. There also you could see 3, 4, 7, 9, 11, 19, 35. It's not exponentially increasing. Even my noise is going from 5% to 50%. On the other hand, if your samples are number of points you need to pick are increasing, this increase is more drastic. Nevertheless, for suppose for example, now you compare it with the Huff transform, where if your number of parameters there is equivalent to the S here, is it not? For example, for a line s equal to 2, for a circle, you have the center, x naught, y naught, the radius, right? So 3 parameters, that's what you have here. And ellipse, you could go on and on as it is increasing. So if each has, for example, a quantization of m, it would increase with order of m power s. But good news is this is not as computationally expensive as that with the increasing number of parameters. But still, of course, this increase is more than what increase you get in the row wise where your noise is increasing. That's what you could see here. On x-axis, you are having percentage of outliers. It is very well behaved, very almost very stable. Okay, and not shooting up to 60% of noise. But of course, if it is more than 60% of noise, to pick the right guys out of a lot, okay, where there are out of 100, if there are 90, so 60% of guys are misbehaved, so then picking the right person would obviously require a lot more experiments. But good news is as long as it is 60%, because see, only out of all the n samples I'm taking, it's good enough to have one sample correctly among these random things. So that's a good thing here that you could observe, right? So this is a visual illustration of this random sample consensus RANSAC algorithm. For example, this is a translated images or what you have here. So this, you translated your camera and took the pictures. So those which are shown in yellow are the right matches. And so in other words, they are the inliers. And these two are the outliers. So you're matching, they are outliers because the transformation that you computed for those 2 points is going wrong. Okay, that's coming from, you have the descriptors, you run, for example, let's say features you do from Harris. On that you use a feature descriptor of something else. Okay, what is that? You could use shift there, and after that you find out that which has minimum distance. Maybe this would have ended wrongly here, this would have ended wrongly here, which you have no clue. but you would say, well, I don't have more than 20% or 50% of outliers in my case. You run this, you pick how many pairs of points you need to pick here. If it is just translation, one pair of points you need to pick, so that you do it now. Okay, suppose you pick this. Okay, and then what you are going to see there, well, that would give you some translation. Okay, within that translation you take a tolerance and see what are the translations for the other points. Okay, don't look at it as now the points here in this spatial domain, but in the spatial domain of the parameters you need to look at. So then if you happen to pick this point, for example, this would become inliers there. Okay, so then you have 1 2 3 4 5 inliers and 2 outliers. Suppose if you happen to randomly pick this one, okay, there will be 2 inliers and 2 4 5 outliers. So all that you need to do in your random experiment, as long as in n number of times you are repeating, it is good enough if you are able to pick one of those 5. So if you pick, that's what would happen. This is how you would be running your thing for a translation. So so line fitting is, or curve fitting is what we have seen for purpose of easiness. But you could see here, if this parameters from those parameters that you are getting there, could figure out what should be the value there. Okay, so to summarize here, the good points about RANSAC is this is simple and general, applicable to many different problems, often works well in practice. This is robust to outliers, okay, because you are doing outlier detection, obviously. Applicable for larger number of parameters than Huff transform. It is not going to blow out exponentially as Huff transform does. And parameters are easier to choose than Huff transform. The discretization and all are more complex there than what you need to do here. And again, you should be in Huff transform, you should be able to come up with the parametric equations that represent that. So essentially you could see RANSAC for two things. One, the curve fitting that we have seen earlier with Huff transform. Second, the parameter estimation. So both the applications you could see separately here. This is bad as computational time grows quickly as the number of parameters. Bad, but nicely the RN Bobic says not so good. That's a better way to say it, because these are not really disadvantages as such. Again, most of the slides from this presentation are also from RN Bobics. Okay, because this obviously is growing quickly here, but not as fast as it does in Huff transform. Okay, then not as good for getting multiple fits. Still the problem of I have points like this. Okay, for again I'm talking in terms of curve fitting, so you would prefer two lines here, but there is no way you could do it in RANSAC. Or you could think in terms of transformations. One object is translated with a different value than other part of your image is, then also RANSAC would fail. Okay, this is something we would do in from the next class onwards when we start discussing about motion estimation. So it is now we are going to venture into discussion about some of the applications. First application being motion estimation. So there we would see that we would model this. Okay, well then this common applications are computing homography, estimating fundamental matrix. Okay, this fundamental matrix is not introduced to you yet in this class. This is where you would come, where you are calibrating two images for getting 3D information. So hold on for that for some time. We would come when we are discussing about shape from stereo. Then every problem in robotic, if you are going to work in robotic vision, where for example you need to separate there is a plane on which the objects are there which are moving, to get that plane separated. I'm not going into that application part, but that's where this could be quite useful. Okay, so yeah, those who are going to work in robotic and control aspects of it, please take a more detailed look at application of RANSAC for robotic vision. So there are quite a lot of applications which, in the interest of time and other topics that needs to be covered, I would skip that. One last point before I move on is there is something more is also done on top of RANSAC. Is once you get 90% of outliers, let's say for the set of 2 points that you have picked up, among those outliers, as a last step, one common thing that you could do is, now for these points you do a least square fit. That would give you, for example, you for the points that you have picked up, or the ones that might not be the best line going through. This might be going through these 2 points, but something other for these inliers would give you a better thing. So people would normally do as a last step to ransack is doing a least square fit of all the outlier inliers that you have computed as a result of this ransack. Okay, so with that I'll stop here.